go. Number one. And of course, after my tirade about not enough momentum diagrams, number one is all about energy. So, how many people had energy bar graphs as their first one? Good job, Paul. Should have had energy bar graphs for this one. It's the conservation of energy one. Most of these are conservation of momentum also, but this one is strictly conservation of energy. All right. So what we need to do is do the bar graph for it. So we got two masses, as shown. That setup is what's called an Atwood machine, and it's something developed by a gentleman named. Any guesses? Atwood, yeah. To actually study acceleration, to demonstrate acceleration, which will be our next unit. But we can look at it through the lens of energy. So we're given it and told that it moves, the big one moves down, the small one moves up. Find the speed of the masses just before M2 lands. And in terms of the other ones. And then also evaluate your previous part using these values. All right, so we need to look at the left-hand situation compared to the right-hand situation. In the left-hand situation, we have a lot of gravitational potential energy. All right, so I'm going to label this column as PE grav. Any other type of energy there on the left-hand side, if they're stationary? Is there any spring energy or anything like that? Nope. And then, so then M1, or M2 goes down and M1 goes up. And they're going to change the amount of energy they have. But let's start off, we'll give it a high amount of PE grav. All right. Is there any external work done as it goes from the initial to the final, do you think? Nope. So we got the same amount of energy to use over on this other side. Are they going to have any kinetic energy? In other words, are they going to be moving? Yes. Yes. So, and are they going to have any gravitational potential energy? Yeah. Well, M1 is, but we could say M2 isn't, right? In fact, we could, well, we won't do that on the graph, but. So they're going to have some gravitational, here, let's give it, I don't know, 4 blocks. And that leaves us with 1, 2, 3, 4 blocks here. And so that would be my Y for it, that bar graph. Now, I could even do more detail with, for the first one versus the second one, things like that, but this would kind of be the base. What I might expand on here is say, okay, well, this PE grav is just for M1, and we're going to say this is for M2, and this part is for M1. And you could actually break up the other side similarly. Okay? So, mathematically, we have PE grav before equals KE of 1 and 2 plus G grav of 1. So I'm going to say that when it's at the bottom, when M2 is just before it hits, so when it's moved through, it's gone down, that's where I'm going to set my 0 point to be for my potential energy gravitation. All right? Remember, I can set it anywhere, right? And that's just a convenient point. Could I have set it at the dotted line? Yeah, but then I'd have to deal with negative and positive, right? Since where it lands down here, or just before it lands, is my lowest point, if I set that as 0, then I don't have to worry about negatives and positives. Okay? So, looking at the before, each of the masses is raised up a level h. And so beforehand, I'm going to have P of 1 plus P of 2. And both those are gravitational. Sorry, I should have had the G's in there. And then I already have this side out. Whoops, let's expand that. They're both going to be moving in the second case. But only mass number 1 is going to have any potential energy. All right? Now it's just remembering my formulas, right? The potential energy graph is mgh. Kinetic energy is 1/2 mv squared. So this would be m1 g. And at this point, it's at a height of h, because remember, I'm taking that bottom position as 0. H plus m2g times h equals 1/2 m1. Now, think about how fast is M1 moving compared to M2 in our second situation. I've heard twice and half and same. Which do we have most support for? I heard a couple same. I heard same is the correct answer. Think about the rope. If M1 was moving faster, what would happen to the rope? It goes slack, right? Because it's moving faster than the rope's moving. What if M2 is moving faster? What would the rope have to do? Split or stretch, right? Like if you had a bungee cord, that could happen. But for the rope to stay taut and not stretch, they have to be moving at the same speed. They're one object really moving together. So I'm just going to call that V. And then this is M1G, and it's now not at a height of H anymore above that bottom, but a height of 2H. And of course I've run out of room. Yay! Because now it's just algebra, right? What do they want me to find? Okay. So they want me to solve this for V. Right? So it'd be maybe, do you guys need me to do the math, or do you think you can do it? Okay. So how are we going to get V by itself? Because that's what solving is, right? Let's first get any term with V on, leave it, and get everything else to the left. Okay? So everything else to the left, would be M1GH plus M2GH minus 2 M1GH. And that's going to equal 1/2 M1V squared plus 1/2 M2V squared.
Is it minus 2 M1 on the left side?
Yep. And let's see. Oh, I can minimize this. Say M2GH minus M1GH, right? And then this would be V squared times 1/2 M1 plus 1/2 M2. Yep, so now I'm going to further isolate B, right? I'm actually going to pull, I'm going to do two steps at once. 2H times M2 minus M1 all over M1 plus M2 equals V squared. So I brought the parentheses from the right-hand side down and under, pulled the 1/2 out front, which made it a 2 up top, and pulled the H out front. Just so I can write less. And all that's left is taking the square root of that, right? Yeah. Ah. So when it says, like, in terms of M1 and M2 and H, your answer should include M1, M2, and H. Yeah. Yeah, whenever a problem says solve in terms of, that means, hey, we're giving you a license to keep these things in your answer. Yeah, well, the square root of that. Right? Because you're going to end up with the square root of 2H M2 minus M1 over M1 plus M2. That equals the speed. All right, so on to number 2, and another conservation of energy one. So we have a skateboarder, and they start at point A and rise to a height of this above the top of the ramp at point B. What's the skateboard's initial speed? So at A, now what does it mean that that's the highest height they get to at B? What do you have? What has to be true for that to be the highest height? Their velocity has to be 0. What else would be maximized at that point? Potential energy of gravity. So we know they stop, they have no kinetic energy, and it's because the gravitational potential energy is maxed out. So, and at A, they're going to have both some gravitational and some kinetic. Where do you guys want to set the potential energy to be 0? The gravitational. Yeah, let's set it at point A. Right? Because we can set it arbitrarily. Since we're not concerned in what they do between A and B, we only have to look at A and then forget everything else and then look at B. We don't care that they go down. So, that would mean we need a PE grav here. So at the initial, they're going to have, let's say, kinetic energy like this. No potential because we set that, gravitation, we set that at 0. No external work. At the end, no kinetic energy. So that means their PE grav would be like this. And there's our Y done. Yay. And that leads us right here. KE at point A must equal PE grav at point B. 1/2 mv squared equals mgh. Oh, nice. The m's cancel. And what am I looking for? Speed, right? And I've got 2.64. So, oh, I can just, I am recording. .64. Yay! Most common mathematical mistake will be not square rooting. Yep. All right. So let's look at number 5 here. This one does require our before, during, and after diagrams. So it's number 5. The giant egg exploding. Right after Shay taking the slap shot. So you probably the only writing you need to do here is something like momentum is conserved. During the explosion. Is energy conserved? Well, let's ask, is kinetic energy conserved? No. Energy overall is, but not necessarily mechanical energy. So we're not even going to concern ourselves with the energy here, just the momentum. So beforehand, we have our egg, and it's at rest. So how much momentum does it have? There's my drawing for before. For during, I need to draw impulses, remember. So the impulse come in pairs. They're equal and opposite. So J on part B, J on part A. Not my best vectors, but. And then my after diagram. These would be momentum vectors. Momentum of A, momentum of B. And that would be my extensive diagram. Artistic talent notwithstanding.
Can we do number 4?
We ain't done with 5.
Sure, we done with 5? We
No.
go? Oh, okay.
Can I explain it quickly?
Sure. Come up here though, so the mic catches you.
Okay. Does everyone count as the same one?
Yeah, but you gotta be here.
Okay, hold on. Oh. Okay. All right. So.
Now you're gonna explain it.
Right.
The idea behind it.
Right.
Okay.
All right. So for everyone gets part A, you got that?
Right.
Part B. So during the explosion, the force of piece A and piece B has to be equal to the magnitude of force B and A because
Because forces come in pairs.
Right.
Yeah.
Forces come in pairs.
Force.
And then, momentum is Alright, and then for this one, because they're going in the opposite direction, and it says that the momentum is measured to already be 500, going in the opposite direction would be negative 500.
But why would they be equal?
Because
These aren't forces.
momentum. Conservation, yeah.
Conservation of momentum. Because what's momentum before?
5.
No.
What?
Zero.
Zero. So what does momentum afterwards have to be?
Zero.
Zero. It is. I was surprised you guys asked for 5, but that's okay.
7?
I don't know. I have to look at the chart. But I've heard 7 and 4. All right. So number 15. And you've got 2 curling stones collide on an ice rink. Stone 1, stone 2. Now they hit dead center. I'm going to have to make one assumption because they don't tell me it's not. I'm going to make the assumption that this is a perfectly elastic collision. All right? Because if I don't make that assumption, I can't solve this. It's unsolvable, and I doubt that they would give us an unsolvable problem. So I'm going to put that right away in my y here. So perfectly elastic. Thus, momentum is conserved and kinetic energy is conserved. Got to draw curling stones. It is. When we look at this stuff in 2 dimensions very soon, I'll include some curling videos. How do they label? 1 and 2? 1, 1, 1, 2, 2, 2. So, momentum of 2 afterwards. Impulse of 1 on 2. Momentum of 1 before. Impulse of 2 on 1. I'm going to predict that are they the same? How do their masses compare? 21 and 16. So I'm going to guess, and I may be wrong, that number 1 is going to keep moving forward. So when I set up my equation, I'm going to go under that assumption. If it was lighter, I would think it would bounce off. If it was the exact same mass, I would think it would stop. And if I'm wrong, I just get I'll get a negative sign on something where I wouldn't expect it. But I think I'm pretty good. So that's the diagram you should have. I'm going to use my 2 little facts up here. That momentum before equals momentum after, and the kinetic energy before equals kinetic energy after for the whole system. Oh, one of you had an example problem like this, right? Yeah. Yeah. Yeah, one of you did. So this would be momentum of 1 equals momentum prime of 1 plus momentum prime of 2. Switch colors. Ke of 1 equals Ke prime of 1 plus Ke prime of 2. The prime just indicates a different value. So M1 V1 M1 V1 prime plus M2 V2 prime. Just means a different value. So we could call it V1. In fact, we'll switch it, just because I know it's bugging some people who take calculus. We'll switch it to V1 final, V2 final. How's that? Okay. Time just means different. I know, you have your mindset in one way. That's okay. I understand. 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. There you go. 2 equations, 2 unknowns.
2 unknowns.
Yeah. You know M1, you know V1, you know M2. You're only left with V1 final and V2 final as unknowns. You know 1/2 also.
Wait, there's which 2? Are we using the blue M1 V1 and the green half M1 V1?
Yep. 2 equations, 2 unknowns. Drop them together into like Wolfram and have it solve them for you. After all, it's not math class. So.